Right. Where was I? Sleepy. Um, right. Priority queues and buckets. All right. So, do you want me to just type or do you want me to talk through it? I have no idea. Whatever. Um, million billionaires. I think the last thing I did was commit. Not seeing any commits though. Oh, here we go. Start on full scheduler. Got to go now, but this is the next work. Okay, right here. I got to pull context back into my head. But basically, I've realized that slow events. Get some lights on. Slow events are going to have the exact same types as fast events. They're not going to have like different things. So we can get creative. But basically we can be like, okay, when a computer boots on, maybe like someone that checks once a month, what they can do is when they boot, they can schedule a network call, and then they can do something based on the results of that. And then after that network call, they can shut down and then schedule a boot up in like a month. And that's all possible. So it's a client awake, client boot, etc. Slow events. Okay, so they're gonna have the exact same types, which kind of solves a little bit of a problem. But the another thing I realized, and actually made a note about this by opening a new tab in Safari. Here's the exact note. Slow events must be converted to fast events when they get in range. But the question is, do fast events have the same type? Yes, they do. Yes, they do. Now let's see where the fuck I was in all this. Okay, so when we pop, we get the next event. This is pretty obvious. And then if it's a slow check event type, we need to reschedule the slow check event type. That's it. That's all we do. We don't actually run anything here. We only reschedule the slow event type because. Oh, wait a minute. But how are they going to get scheduled? Okay. Okay, never mind. All right, here's what we're going to do. This needs to take the current time, turn it into seconds, and determine and potentially push slow events into the fast scheduler. So let's say we schedule something like a month out. That's not going to get scheduled. But let's say we schedule something a month out, and then we keep going through the fast event, and eventually the time has come. We need to do something like UINT, probably 64 type. Current time is equal to. Oh god, this is actually. This is actually a pretty interesting one. It's something like cycles through buckets times okay, we need buckets. We need bucket bits. Okay, bucket bits is 3 times bucket bits plus priority bits. So okay, I'll just type out the diagram right now. It's like, what is that, 20 22. I don't know what the hell this is. Real time 22 maybe. And then we have, actually I can make this realistic. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. And this is 3 for bucket, and then 29 for priority, or 39 for priority. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is what the real time actually looks like. I'll do R, priority. Okay. So current time is equal to cycles through buckets. So that gets multiplied by a big number. Then we have plus which bucket we're on times p bits. So this is like this part of time. And then we have plus priority, which we'll get to those in a second, but whatever. Oh, wait a minute. Priority is just... I really need to make this more explicit because I'm just looking at this the next day like, what the fuck does this even mean? What are all these numbers, bro? What are these numbers? Okay, whatever. Oh, it might really confuse me that bucket bits is the same as event bits. We said event bits, right? E-bits. E-bits is... oh, we need type bits. We need it shouldn't even go here, but uint 8 type t type bits. T bits is equal to 3. Okay. So we got this whole fucking thing. So that's current time. We do something like if the way these must be scheduled. Let me write this down actually. The way that slow checks must be scheduled is that they are scheduled as far... Wait a minute. They're always just going to be like max. They're always going to be... These slow checks are always going to be pushed out or rescheduled as far as possible, which is... I believe the max is... what the fuck is it? Here, max delta. This is max delta. This is as far out as we can schedule one of these buckets, and I think that's how we're going to schedule them. The only question is, so any slow events. Oh, I guess we can just keep popping slow events, huh? Yeah, we can just keep popping slow events. That's not even a problem. We keep popping slow events until... Let me write this down. This is a lot harder than I thought. So right now, scheduler. Fast and slow. So right now we're at some time t. Maybe... Okay, we're at some time t, and we have some time t plus that max delta. We have some t plus max delta. And then within that time frame, we might have some slow events represented by seconds in the other scheduler. Okay, what we need to do is take all the slow events between now, so Okay, so there's a bit of a rounding error here. Let me think about this. Tmax delta, I think this has to align to a specific second. Let me think about this. Okay, let me zoom in on that Tmax delta. So we have, okay, we have like a true Tmax delta, but then we have like a, when we divide by a billion, because this is nanoseconds, we need a 1, 2, 3, 4, 5, 6, 7, 8, 9. Once we divide by 1,000, we're actually going to crop up. So we're going to have like a cropped max. And because the slow events are in seconds, it is very possible that we have a slow event scheduled exactly for that crop max. It's possible that we also have a slow event scheduled on exactly... It's possible that there is... wait. It might just be the case that we go through and it lines up that t plus max delta is exactly on a second. It's not likely, but it's possible. A slow event could be scheduled exactly on that second, or it could be... It'll always get cropped. Whenever truncating will always go down. It can't go up. If we have something scheduled the next second, we can't schedule it right now. We can't. So that's fine. So if we have a slow event, okay, let me do this. UINT64 type truncated second is equal to current time divided by 1,000. So this is basically time in seconds. Time in seconds. If a if an event is greater, if a slow event is after ns max delta, we definitely don't put it into this. If it lines up exactly with ns max delta, i.e. Truncated t times billion is equal to current time, what do we do? If it lines up exactly with the max delta, I'll come back to that one. If a slow event lines up exactly with the truncated second, so that's fine because we can take that second, we can multiply it back by 1,000,000, we can multiply it by 1,000,000,000, and then we can put it back into the scheduler. We can multiply seconds by 1,000,000,000 and put it back into the fast scheduler. Now the question again is, what if it's exactly on the max delta, which is extremely unlikely, but maybe. What do we do? Because if it's at the max delta, then I think we should if it's at the max delta and we try to reschedule it, it'll work because wait a minute, I just realized something. We better be max delta delta nanoseconds. What is delta nanoseconds? Okay, good. So we aren't reading it directly from event. Never mind. I just was worried about something. If we schedule it at the same value, well, because actually this is kind of hacky, but it does work. This is kind of, it actually works. Where is it? This is weird and relies on slow check equals 7, but it will work because we then schedule 2 events at the exact same time, the slow check and the slow event converting to a fast event. But because the fast event or the slow event was not, like, you can't schedule a slow checker in the slow scheduler. That can't happen, right? No, it can't happen. If that's the case, oh shit, should we get another one? Nah, 17,000 years is enough. Cropped max. It's weird. I'm leaning towards actually scheduling the checker a bit early and not scheduling this one. But even then, what happens if the slow checker runs first? If the slow checker runs first and then the actual event we need runs, maybe it doesn't actually make a difference because the slow checker can only schedule future events. It can't actually do anything. So if we schedule future events, oh, but then what if the slow scheduler needs to schedule something that's happening at the very same instant? Could that be possible? We get... It can't. It can't schedule something at the exact same instance because it would have been converted into a... it would have been converted into a fast event already. Oh my god. Yeah, I'm still leaning towards I'm leaning towards just like bumping the wait. If we turn back, like let's say we rewind by 1 second, so we'll check the slow scheduler 1 second before that event that lines up. We might just hit another event. Then what do we do? Yeah, wait. Well, we can schedule the other one. We can convert the other one in... Oh, wait. Easy way to solve this. We just... Yeah, you know what? Maybe we just put it... But the order doesn't even matter. It doesn't actually matter. Because slow checker won't actually modify market state. Alright, fuck it, whatever. So if it's equal, we'll line up. If not, okay, so the question is if so we have cropped. So if it's equal to, if something, what is it? Current time. If something is less than or equal to truncated seconds, then we go ahead and schedule it in convert from fast to slow to fast. Else don't schedule it yet. And then yeah, and so this way we can just keep rescheduling the fast scheduler. Yeah, we can just reschedule. We can keep rescheduling the slow checker in the fast scheduler. Now the other question is, what if we just every time we every time we popped from the fast scheduler, what if we just checked if we went up a second? That could work. But I don't know. Maybe. Alright, so what do we actually need to do? We're gonna peak and pop from, yeah, we're gonna peak because we don't want to pop anything from the slow scheduler unless we're sure. So from slow scheduler until we meet until something greater than truncated second. Okay, cool. So while just write this out, uint64 type, wait, this isn't even, I just realized this isn't, it'll pop the full event, it's not going to pop the PS peak. We'll do, what is it, scheduler, what do we call it, slow bucket, we're going to peak it, slow bucket, and then we also need to do peak timestamp. We need to shift it by event. So we need to get the bits, we just shift by event. Okay. So this will give us the timestamp, and then this is the easiest way to get it. Okay. If peak timestamp is less than or equal to truncated seconds, because this is in seconds. The other one is in nanoseconds, this is in seconds. So if it's in truncated seconds, or less than or equal to, then we put it into the fast scheduler. And this will also mean that if we have fast events, or if we have slow events scheduled on the exact same second, that could be a problem. Oh, wait a minute. Now that I think about it, I think we did have something talking about different slow events. So this is kind of well, do we have anything about slow events? Oh, here we go. Slow scheduler events. I wrote that they are the same, but then I crossed it out and said delivery of order and EOM EOD handler. Right. I think okay. There are some events that require special handling. However, I think they are best handled as type 0 client toggle, but with the server ID of 0 as the client ID. And then it will be up to the server it's rare. It's rare that this happens. It's once a day, once a month, which if we're going to be simulating like some kind of high-speed nanosecond trading, it's rare. So I don't think it's a problem if we have some method that goes, okay, here's the current time. Is this the end of the day? Is this the end of the month? I think that should be fine. End of the month is going to be fun, of course, because 30 days, etc., etc. But that seems to be it. There's also delivery of order, which is, I wonder what that could possibly mean. I mean, delivery of order just sounds like client. It's like an order response. Oh yeah, type 6, order book delivery to client. I don't see anything else for a slow check. Oh, wait a minute. Wait. Or even we could schedule type 7 slow check events into the slow scheduler. But we'd have to be careful to make sure not to oh no, we do want to reschedule them actually. We do, because we'll have a slow checker. Then we could also have a special. Okay, this is basically what the slow checker is going to look like. We're going to have 39 bits of numbers, you know, something whatever priority. Then we're going to have 111, which is 7, and then we have a bunch of 25 bytes, I believe. Yeah, 39, 42. Yeah, we have 64, 29. Wait, 39 priority, 42, 42. We have 20. Yeah, we have 22 bits of priority. We have 22 bits that are just unused. We could say like month. We could put the ASCII string month in here or day in here, and we could put both of them in there. Type 7 events have lots of space, lots of unused space in them. Yeah, I don't know. Yeah, we'll see. Hell, we could even. Yeah, that's not even a bad idea. But we'll get to that when we need it. More on this later. If we pull a type 7 event from the slow schedule, that means there's something special going on. Must be the end of the day or at the end of the month or something. So we'll handle that. All right, cool. What's next? So while if it's less than or equal to the truncated second, so it is within the limits. It is within the limits that we can reschedule. We then take the peak timestamp and we put it into the scheduler. So what we need to do is we need to take the UINT 64 type we'll pop it. Okay, so UINT. We don't want to pop it prematurely, but UINT pop is equal to PS pop slow bucket. So we will get that guy. We will get this guy, and it'll shift all the slow bucket stuff. And then what do we do with this? We preserve the E bits, so we do need to do something like pop and pop is equal to pop and emask. Emask. So emask. So that preserves the actual event. So the type and the parameters for the type. But we need to completely reassign the timestamp. The timestamp is going to be it's going to look like peak TS times a billion S to nanoseconds. With this, we need to reassign. We need to modify the timestamp to fit in the slow scheduler. Oh wait, we could just call this again. Where is it? We could just call schedule fast. We have the event, and we just need the delta in nanoseconds. And delta in nanoseconds is going to be wait. We're not. Okay. Let's see. So we're at some time t. This is like some amount of nanoseconds, and this is. Wait. Okay. Hold on a second. Getting the event is easy, but the timestamp is it's not simple enough to just wait. What do we actually do? What do we do in this method? We've already figured this out. We know that it's the slow event is early enough that it's gonna fit. We have bucket delta. Oh, we do need to do bucket delta. Maybe we do need to like figure this out. What is the delta in nanoseconds? What is the delta in nanoseconds? Well, we have the current time, right? We have the current time, and all we need to do is okay. I was thinking we could just figure out the bucket right here, but oh no, we still could. We still could. The real time is peak TS. Peak seconds. This is wait a minute. This is actually much easier than I'm making this out to be. Because they're all powers of 2. Because they're all powers of 2, even if this is oh, it's just this. We do peak timestamp times seconds and nanoseconds. So this gives us the real time in nanoseconds of what we want. Now, this is actually quite easy because we're using powers of 2 for all the wait, are we? No, we're using 39 bits. Yes, but we're using 2 to the 39, really. The time span is 2 to the 39. Let me explain. If you have a node, right? Let me show you like this. You have x is equal to 1 billion, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have, let's just look at like, maybe we're at some time 100 times x. This can represent like real time, okay? So if we do, how do we figure out what bucket we're in? Like what bucket are we going to be in? Because if the buckets are tracking correctly, if we start from the 0 bucket and we go all the way through to the 8th bucket and we loop back around, that means that the number of loops, each number of loop represents how many times we've gone through the buckets. Every bucket represents some amount of bytes, some amount of bits. So it's really, like I said, it's this format right here. Like I'm pretty confident that real time can be represented like so. I just had it here, right there, and it's not real time; it's cycles. Ooh. Cycles. So cycles through buckets. So this is real time basically, and we can split this. All we need to do is do 100 and x, and that. Okay, almost there. That. Okay, I think it's just hating because it's yeah, okay, very funny. And funny enough, this actually tells us exactly which bucket we need to be in too, because we can just do this. Alright, fuck it, I'll just tell you what this is. Okay, we multiply by 1,000,000,000, we do this, and where's the 1E39? P bits. Wait. We calculated something wrong. Hold on. Yeah, right here. Priority bits. Wait, bucket bits and priority bits. Yes. With priority bits. How do we go from this back? Cycles through buckets. Cycles through buckets is not going to change by rescheduling something. Bucket is going to be it's going to be the 42nd to the 39th bits of this thing. So shift it over by 39. And end it with the bucket mask. Okay, and then this is the bucket, but then p bits is just input if you don't have this. There. Okay, so that's it. That's the this is the priority. This is the bucket that it goes into. Now, since we have priority, we can do something like event data is equal to the. I know my context is my syntax is awful, but we basically do priority, and no, priority gets shifted by e bits. We need to make enough room for that. That ORed with event data. Event data doesn't need to be shifted. We already did that. So this is the final event. Final event is equal to that. And then we simply put that into the right bucket, which is going to be, pull up the, where is it here? PS, priority queue, push, something, final event. Or really like fast to slow event, or slow to fast event. What do we actually put it in? It's going to be something like buckets, bucket. Now, this is just a rescheduling. This will not actually advance what bucket we're on or which, how many times we've gone through the buckets. So, next question is, what is the next question? So this is cool. If it's less than, then we go ahead and schedule it. We loop back again. We check its peak. Okay. If not, what if it's not? What if it's past the end? Then we can't schedule it. We need to keep it within the realm of the. We need to keep it in the slow scheduler. It's not happening, not yet. So what we do is we just reschedule, or actually we just break. And actually it's a bit simpler than all this. We can probably combine these, but whatever. And then once we're done rescheduling the slow events. Now we just reschedule the slow checker, and we're good to go. So to reschedule the slow checker, what we need to do is it might be as easy as just calling this method So, because it already has a lot of the work to take care of buckets and everything. So we do schedule, we have event and we have delta. Delta nanoseconds is going to be the max time that we can push it out by. So let me just copy this, see how to call this real quick, and where are you? I'll just reschedule the slow checker, and here you go. All we need to do, we already have SCH, UINT event. This is actually going to be, I mean, all we really need is like the raw slow checker event, and that came a while ago right here. Next, we can just reschedule it, or we could insert it directly, but we already have so many nice checks in the other method. Actually, maybe I shouldn't be lazy. Okay. What do we actually need to do if we put into the fast scheduler again? Bucket span max delta. We basically need to push it out by max delta. First off, delta nanoseconds is already so low. Well, I think these get scheduled every like hour of simulated time, so they are pretty rare. Famous last words. Delta nanoseconds is just going to be it's not equal to, it's not greater than, it's going to be exactly equal to. So all we do is keep an eye on the time, and we put it back right here. Max delta. Cool. Okay. So that's what happens when we have the slow checker in the fast scheduler. If we have a slow checker in the other one, it's all weird. That's when we have the end of day, end of month, etc. We cook up some rice. Okay, what's next? If we do that, what else do we need to do? It's almost impossible that we... Actually, no, it's not impossible. It's not impossible that we pop out a slow checker, we reschedule it, we pop again, and it's again the slow checker, because that's just something that can happen. I think for consistency, we should return the slow checker to the we should return the slow checker to the caller, just to see what they do with it. We're done rescheduling. Okay, so this is the whole 7 case, isn't it? Yeah, it is. Amazing. Don't need this. Don't need that. Don't need anything here, actually. Okay, So that's the slow schedule. Now, what about the normal pop? The normal pop, this is where we actually move time forward and have a bunch of fun with it. So I previously mentioned that we can do cycles through buckets and bucket. This is actually critical for calculating when to schedule these guys. So now nanoseconds is next, but without the event bits. So this is now nanoseconds. Now we have specific restrictions in place to avoid, to basically avoid scheduling future events previously in the same bucket. That is exactly what this line does, and it's the whole reason for this architecture of buckets. So if we pop the current bucket and it's empty, which is completely possible, we need to move on to the next bucket and keep moving on until we hit something, because it could have been just rescheduled only in the prior bucket if we have, for some reason, just no events. Let's which is a separate branch from this. So let's do. We should probably handle this before this. So uint next is equal to pq pop that. What if it doesn't happen? What if it's just not happening? Priority could be 0. That's fine, but maybe what is the 0 type condition? Should we say something like, oh, it's actually probably safer to put this in the type 7. Type 0 client toggle. Yeah, I can definitely see us having like turn on client 0 at this time. Yeah, so type 7 will kind of be a catch-all for a whole bunch of stuff. So let me just make that clear. Type 7 events will be catch-all for system timing stuff. Which will also require us to rewrite the PQ, because we need it to do something when we don't return, when we are empty. So type 7 is also going to cover the case where, but what the fuck am I saying? How do we get static const uint? We need this in 2 places. The scheduler needs to the scheduler relies on the PQ. We can't have both ways, I think. So I think this value needs to go into the PQ. So source, include pq.h, and we're going to have a special value. We're going to call it static const uint64 type empty. What do we currently do? Source PQ. If it is empty, if we pop and it's empty, oh. Okay, what about instead of funny values, we just check if it's empty? And what if we just checked if it's empty? What would that look like? So screw the values. We'll do this can be minimal. We can do uint68 type pq empty. Pq I guess is empty. Pq star pq, and then we just implement it with the exact same signature. All we need to do is return pq.empty. Just kidding. What do we actually need to do? If the priority queue is empty, that means that so some kind of index value is going to be at 0, I believe. So when we initialize it, current is equal to 1. Is that it? If current is equal to 1, that's where we place next, right? If PQ is greater than heap 0. Oh, this is a little hack there I did. Just to save an extra byte in this priority queue, or extra UN64. So if PQ is if it's empty, what properties hold? How's event indexed? Run. What does run start with? PQ. Oh, it's weird because we don't exactly insert it at a spot. When we push, we don't insert it at the back and then swap up. We heap run. Okay, so the first thing we do is we do run is equal to PQ current, and then the first modification to the heap we do is PQ run is equal to that. So the first thing we do is PQ current is equal to run. So therefore, current is kind of like the index of the next thing. So therefore, all we need to do is return this. We're just making it explicit with a function call. This should probably be inlined. There. Let me just see if there's an easier way to do this. Where's the... Here. Make sure the stream's good. Excellent. Good. That's what I want to hear. C boolean. C boolean. Well, it does have a bool data type. std bool. Oh. We'll see if this builds, honestly. If PQ is empty, we should probably update the test for PQ as well, now that I think about it. Okay, VI tests, test PQ. We can do assert. Oh, I don't even know how this works. PQ is empty. PQ equal to 1. We just do, if we push something, it should be not empty, right? Cool. This is absolutely not going to work because the others, shut the fuck up, would you? Let's bring back PQ. Let's just see what happens. It's probably not going to build, but nice. Actually, not as many errors as I thought. So schedule's got a bunch of errors. Okay, well we can just fix that by doing this. Boom. Make test. Hey. Oh, sorry. I don't see any assertion failures. Looks good to me. Source PQ, git add test PQ, git add include PQ, git commit added empty to PQ. Cool, that's super useful. You'll see why. Let me also revert this so we actually test random, and also let's revert the make file. Get the status. VI make file. Skj.o. Okay, let's go back to where we were, so we don't have to deal with any funny numbers. We can just do if PQ is empty. PQ. Buckets current bucket. Okay, so now we don't need to rely on any types or stuff. Never mind. If it's empty, advance until something scheduled. I mean, we could still do like a type 7, like all ones event as like a terminate. Maybe when we hit like the year, I don't know, 2040 or something. But yeah, otherwise, it's a bit hot. Otherwise, looks fine. Let's keep going. There's a whole lot of pseudocode up in this bitch. Okay, advance until something's scheduled. If there's nothing scheduled, we do have a problem, but oh well. Do we always need the empty check? I feel like this just like slows us down, because this is going to be called a lot. This is one of the top things that gets called, and if we slow this down with an if statement, well, even if we have some funny number, we still need to do that, so probably better that we don't. I mean, this is just checking an index, right? Just checking the value of an int. It's not that big a deal. Fuck it. All right. Let's see if we can remove this check. And specifically, what we need to do is, if it's empty, then we loop, not before. So we do while one. We do if PQ is empty, if it's not empty, we can break. Bring back the old do while. How about this? Oh yeah. Now we're talking. I told you this would come in handy. Current bucket. Sorry. Almost forgot. Scheduler. Current bucket. Plus plus. Okay, so bucket. Ooh, you know what I just realized? We could keep the current bucket and the cycles in a single int64. Maybe. Let me think about how that would work. Okay, so there's like a difference of a factor of 8. So each bucket will be what? We decided what, 39 or 32. So so each. Let's take the smaller case. So each bucket is 4 seconds. If we have 16 buckets, that's that many seconds. If we so a minute. So 16 buckets allows for a minute. If we if we store this as an int32, the consolidated bucket plus loop, that allows for 4 seconds times that many seconds, which I think is greater than the number of years we support. So let me try. Let me just do the math on this. Divided by 60 minutes, hours, days, years. Yeah. That. Oh. Honestly, that's good enough. That's probably good enough. So this is like how many years we support with the scheme. Even if assuming 32, if we switch to 39 priority bits, which is I think what we're currently building, we support that many years, which is way bigger than the other number. Let me show you the other number. The other number is, if we have this is for the slow scheduler. Slow scheduler supports that many seconds, which is yeah. Oh. What? Wait. That's how many seconds are supported by 39 bits in the slow scheduler. This is how many. This is how many like loops are supported through the if we keep it as an int32. If we keep it as an int16, this is how many years this bucket loops thing supports, which is not even a year. Oh, because I spelled it wrong. 11 years. Yeah, people know how much 11 years is. Okay, so cool. So we definitely need a 32-bit int, so we can do current bucket. We just need to make sure that every time we schedule it, it goes into okay, let me make a important note. Current bucket is actually like buckets since start. Need to do and7 to get current bucket index, or 3 to get bucket cycles. Okay, cool. Which also simplifies the current time equation, but we'll get to that. Cycles through buckets. Okay, so the only thing we need to be careful of is something like bucket mask. There. What else do we use current bucket? I'm starting to see the problem with this. Oh, wait. Cool. This is exactly right. Let me see if there's anywhere else we do current buckets. Surely we do somewhere else. We do it, no? What do we actually push? Right, bucket's bucket. Oh, we already do bucket mask anyways. Whatever. What the hell is this? Resulting bucket. Resulting bucket is also okay. Cool. It's probably good enough. I don't know. So cool. We have a way to track the number of cycles through the buckets and the bucket we're on all in one foul swoop. This will be important for translating between the slow and the fast. I think that might be it. I don't know. Maybe I forgot something. Oh, right. When we actually pop, if it's not the case that it's a 7, and this is a fucking mess. Maybe make it more explicit. Yeah, that 3 is not the same 3 as the buckets. That's going to confuse me. Okay. Yeah. So if it's not the case that it's this, I honestly think we should return. And we still return next. We just do something else with it. Or actually, maybe we don't even need to do anything. Oh, wait. Now, the question is, do we even need to do now nanoseconds anywhere? Do we need to store now nanoseconds? Because I don't actually think we do. And with the bucket thing handled above, we don't actually need to do that either. So I don't actually think we need to do anything. We just return next and call it a day. Maybe might be better to return actually next and emask, but oh well. But yeah, why not? Yeah, because we don't need to worry about the priority. Or do we? Nah, I'll keep that as a note. But maybe some EOM or EOD events need them. Need priority. Priority. Well, that doesn't even give you the real time, does it? Because when we finally pop the, when we pop, let's say we have a monthly event scheduled, right? I guess we can just tell them it's a monthly event, but we also do need a way to get the real time. And the real time, if we want to be super specific, because, each bucket is 4 seconds, so we want to be, down to the second. We actually do need some way to get current time. Okay, so we do need this. Okay. We actually do need this. Now nanoseconds. I guess it's more like, yeah, technically like nanoseconds. Technically nanoseconds into the bucket. So this multiplied by 2 to the 39. No wait. This plus bucket cycle times 2 to the 39 will give you the actual time. Cool. So that'll pop the bucket. Possibly unneeded. Okay, cool. We can also do something like, while we're here, we might as well do UINT64 type. What's the max? Okay, so I know that we can support with 39 bits of priority. We can support up to like 17k years. But what about nanoseconds? What can we do? This is just this, except that. So that's how many nanoseconds. That's how many seconds we can support. This is hours, minutes, hours, days, years. Okay, so ooh. So we can only support 584 years if we're representing it in nanoseconds. Which is a crazy problem to have. Well, this is how many seconds we are supporting anyways, so they're comparable in magnitude. If we go down to 32, I think we get a very similar number to that. Yeah, 136 years. But we're going to go with that larger number for more priority. want to eat that rice. Using the tiniest little fork I've ever seen. I say, damn, so past 84 years, 584 years, we do actually need a way to, I don't know, cycle something. Fuck it. Only supports 585 years. What a shame. What a shame. This is going to be return now nanoseconds. So we, is this going to be like the last event we popped? Yes it is, because maybe we get like a end of, we get an event, and then when we log it, we want to get like what we want to get some information about what we just got. So this will definitely be this. Okay. Yeah. I'm starting to think we actually, in the 7 events, we can store how many seconds until we show it again, but that might be a bit more complex because days and months aren't always the same value. Alright, whatever. Now nanoseconds. This is what is it? Current bucket. Key bits. Yeah, that's all we need. I think that's it. So this is how many, this is multiplied by the bucket span, then we have how many nanoseconds into the bucket. Cool. Let me just add that to the type, and then we can probably start testing this out. Why did you do that? Oh god, someone's already got it open. Okay, who's got it open? There. Oh my god, okay. That's the first one we had. Let's get all the other ones in. And let's actually start compiling this thing, because that's going to take a while too. But you see how easy it is to, you know, once you have like the basic smaller steps, you can use them to build larger steps. This one is probably the most critical of all. This one actually moves time forward. You went 64 type shit. Schedule slow. Is this even used? I think like, oh it is, okay. We didn't fully flesh it out, did we? Let's just copy it anyways. We definitely did not fully finish this one. I think we still had a lot of to-dos. And then this one, there we go. And there. Cool. All right. Let's actually implement the slow one. I don't think it'll be called directly. I think we just call like 1 month in nanoseconds. We need this monthly event happening. Okay. Oh. Actually looks pretty good. Yeah, never mind. Actually looks fine to me. Okay. Let's get the test running. No, not BS, the other one. Include test scheduler.h. Oh yeah. Test scheduler. Okay, vi test scheduler.h, and we just do a cat. Why did you do that? All I need is something along these lines. Thank you very much. And do endif, and then gg, and then we'll do scheduler. Okay, test scheduler. Okay, let's just start with complete basic. And let's see what happens. It's gonna be like, you've got some nerve. You got some nerve calling make test. I know. Oh, there's one more thing we need to do. And oh, it's already there. Okay, cool. Make test. Too many errors. All right. Sure. Why not? Talk to me. There's only a few in the .h file. That's pretty good. We could solve all these really quickly. Hold on. In the source file, what do we need to do? What's the situation? Stop doing that, please, would you? Oh, right. We didn't define it at all. How do we usually do it? Like this. Okay, type def scrub. Yeah. Type def. Don't we need a? Yeah, we do. Type def struct something, and we'll do if not defined h and define and if. Okay, that should solve most of these. Too many errors. Too many errors. That's how much. Okay, there's only 3 in here. That's good. All right. What's up? What's up? What's up? Mm-hmm. I don't know. I don't know. For now. Okay, I guess p bits needs to be in 64, right? Is that the problem? No, it's even worse. Wait, I didn't save it. Hold on. There. Try again. Static non-void function does not return a value. Oh, this is in the C file. Okay, so there's only 2 errors here, and they're both on line 12. Does not like that we're doing this. Result is that with type int. Okay, so what? Shift count overflow. Uh, Shift count is greater than or equal to the type. How is that possible? Because I'm pretty sure that... Wait. Oh, it's the one, isn't it? Well, if you're only computed once, fine. I guess you can do this. There. You can stay, oh, can I just tell you? No, it's only done once. It's fine. UINT8 type. Oh, that's gonna fail. Fine. 64. Everyone's a 64-bit now. You good? Yes. All right. Cool. Cool. Very happy for you. The header looks good. Now let's look at the source. Never mind. Someone has it open. Not you. Not you. Yes. No. Not you either. Where the fuck are... Oh, here you are. Scheduler. What's up? We got so many errors. So many errors. Let's start with the last one. Notes. Okay, so we do need the H file. Never mind. Let me bring this back. Scheduler.h. We do need a buckets. Now, what is a bucket exactly? That's a great question. This is going to be of type PQ star buckets. Buckets. There you go. You happy? No, that's just a typo. Sneak that one out of there. Talk to me. Alright. Oh my, what the fuck is going on here? Place parentheses around the AND expression to evaluate it first. Oh, it doesn't like that we're doing this. Is that right? Okay, that's it. Fixed it. Beautiful. What's wrong with you? Current bucket. Right. Yeah. Okay. Current bucket. You're right. It's not. Should be like this. Okay. Next. Free. What do you want? There. Happy? Now nanoseconds. Now nanoseconds instruct. I would just call it now. And probably a UN64 type, I don't know. Where was it? Now nanoseconds. Where? Just now. Okay, next. Oh, there's another one. Hold on. There. Ooh. Should be a comment. Oh, actually, we're kind of getting there. No, we're not. All right, 174. What's up? PS peak. Oh, of course. My apologies. Now you're being annoying. Clear that one. Okay, still a lot. Unknown type PQ. Well, we just include. Oh no, we didn't include it, did we? Fair enough. We just. Now what? 8. Return malloc size of. Yeah. Obviously not. We still need to do something. Oh, actually, no, wait. If everything's set to 0, everything's set to 0 should be fine, right? Malloc with set to 0. It's like call lock or something. Call lock. I was right. Why is call lock? Oops. Oops. I mean, there we go. Wait. Num objects of size. Whatever. It's only a few pointers. Alright, you return a value now. Congratulations. Make test. What else you got for me? Make test. No such member named current nanoseconds instruct CH. Well, there should be. What are we using it for? Current nanoseconds. Oh. Okay. So what I think is going on here is that we just popped an event, and then sometime later we want to pop an event that derives from it. So we need to. It has to go like. How do I want to do this? Okay, so at some point in the code, we send a message from the server to the client. We pop the send out event, we do some math, and then we want to say, some amount of seconds after it gets sent, we want to deliver. So current nanoseconds is exactly this value right here. So it's a good thing that we have this, because this is exactly what we need now. Cool. What else do we have? Bucket delta. Just kind of threw that out there, huh? Some p bits. Yes, that is correct. Although do we even need this? It's only used. Okay, it is used there, but I guess we can inline it and maybe avoid a bit of assignment. Yeah, so we can swap that out. Bucket is, I guess, UI. If it's and bucket mask, it can be a UINT 8, but this restricts us to 256 buckets, but let's see what happens. There you go. What else? What the fuck is this? What is going on here? Oh. We need a. Wait, but buckets should be. Buckets is an array of arrays. There we go. I think this is the syntax, right? Or whatever. Check this out. It is gonna break something, but it's okay. All right, 31. What's the problem? We can't shift by p bits. Well, that's great because we already did. P bits. Maybe static const uint64 type p span is equal to, again, uint64 type 1, not just a regular one, a 64 type 1, and do p bits. We can do p span, or is this, yes, this is exactly what I need. Okay, so we can do p span, we don't need a, p span. And this is specifically how, like, what is the range of timestamps we can encode using some amount of bits. All right, y'all good? Y'all good? All right, next dumb question. What do we got? Too many of them. Still a lot of errors coming. Okay, 99. What's the problem? Undeclared identifier current seconds. Yeah, I really pulled that one out of my butt, huh? Current seconds. Wait a minute. This might be more complicated than I thought. And this is important because this is how we reschedule events. Okay. Instead of delta seconds, I think we should just say, like, this is exactly what time we want. How do we do this here? Push, buckets, final event, peak and pop, event data. Where's this slow rescheduling? PQ push, bucket, final event. This is how we reschedule the proper event. We don't actually reschedule. Oh, here we go. Oh, we push it into schedule fast. We don't. Okay. So we reschedule the slow checker using the fast scheduler, which makes sense, but eventually, but when we do get new slow events or further out events, we do need to handle them properly. And it looks like current S is probably not efficient to compute, so I'll come back to that one. Oh, no, we use it a lot, huh? We really rely on this current. Okay. Wait, what the hell is going on here? What is this? What did I try to write here? What the fuck? Okay, hold on. Well, first of all, we already have, we don't need this. We don't need another one of these. So however I was going to use it, we just need it as p-span. So that gets rid of a few warnings. No member called slow bucket. That is actually a great call. Great, fantastic call. PQ star slow bucket. Fantastic. That one's an easy one. Still a lot of. Oh, actually no. We're down to 4 warnings and 18 errors. Nice. Well, let me simplify that thing around 161. Cycles through buckets and buckets. This is going to be simplified to just scheduler current bucket, not with the bucket mask, just there. That's how many buckets we've gone through. That's how long a bucket is. There. This is nanoseconds, and then plus priority. Plus priority is whatever we just popped. What did we just pop? Whatever we just we probably did this somewhere, I swear to God, but next. There. No. There. Yes. There we go. I think this is the current time. So this is current time in nanoseconds, and we can just wait. Now is okay. That's now nanoseconds. This is a different now. That's kind of unused. Okay, but this one's more accurate. I'm pretty happy with this. Current time is current time. Go. Actually, it's the exact same calculation. Or is it? Is times or shift faster? I don't know. Alright, we're down to 15 errors. Did I mean PQ pop? Yes, I did. What are you doing? 14 errors. Did I mean PS peak? Yes, I did. Is an easy one. First of all, we already have it. $13 errors. No warning. Oh, one warning. Let's see 196. Undeclared final event. This is a UINT64 type final event, and it can just be pushed into final event. That is perfectly fine. Actually, we can inline it. It's not a big deal. There. Put in the right bucket. Yes. There. That should solve a few issues. 11 errors. Cool. Event data is not defined because event data is this. We don't even need it. Now we're down to 9 errors. Unknown type U in 64. That's a silly one. Everyone knows I meant that. 8 errors. Okay. 194, what's going on here? Priority. Priority. What the hell do you mean priority? Oh my god, wait. Why is... Oh, this is, peak timestamp times seconds to nanoseconds. So we have some ridiculously far out, and then we just take the lower 39 bits of that. This seems fine. I don't have a problem with this. This is a UINT64 type priority. And then we also have a bucket. Oh, we just directly compute bucket. We don't worry about anything else. This seems fine. This is a UINT 8, maybe an 8. Actually, let's extract this one out. UINT 64 64 type seconds peak TS times passing 2 nanoseconds. Let me just swap that in. Don't you mean pop? Yeah, I do. Wait, no. No, I was right. A few bit operations here. I think that should be fine. Let's see what happens. Okay, cool. Down to 3 errors. Use of undeclared identifier current bucket. That makes no sense at all. What do you mean? How's that? Happy? 2 errors. Let's go. 198. Okay, they won't let me off the hook. I need to figure out what exactly to do in a slow scheduler. Let me see how it's called first and foremost. Delta nanoseconds, seconds, and nanoseconds. I think you might as well just... Delta nanoseconds. Okay. I think we should do all the conversions here because it's, you know, it's slow. It'll we can just do UINT64 types delta seconds equal to delta nanoseconds divided by what is it? S2 NS. Okay, so we have delta seconds now. What do? We now need to figure out, well, to schedule it in a slow scheduler, we need to figure out the exact, wait a minute. This loses this loses resolution. So let's do this first. We can do this. What is it? SC now? Yeah. We can do now NS. So this will give us the time now in nanoseconds, but we want something super far away, which is going to be delta nanoseconds. And actually, I think now that I think about it, I think we already figured this out. Max delta nanosecond. No, we only do max delta and delta nanoseconds. We don't deal with absolute time here. All right. So for slow scheduling, we have the now time in nanoseconds plus delta nanoseconds. We now have UINT64 type requested nanosecond absolute nanoseconds is equal to that. So this is from the start, how many nanoseconds we want to simulate, and then we have, what do we want to do? Then we just take that and we put into the that's the priority. That's the priority we need right now. So schedule event just needs to be absolute nanoseconds divided by seconds to nanoseconds. This is a bit of a mess to do. Hold on. UINT64 type absolute seconds is equal to absolute nanoseconds divided by seconds to nanoseconds. Okay, cool. Now there's only one bucket. Now the problem is, it could be the case that this will silently fail. And anything that gets scheduled super far into the future will actually go into the past, because it'll like loop around. We can only support like what, 584 years. If this, how can we check this? How can we actually check this? If the difference between max and well, the whole point of the slow scheduler is to give us more time, but we could still, if we're at the end of like the years and we request something, a really high number in nanoseconds, we could still go above the value. So what are we actually looking for? What is the actual value we're looking for? Well, let me ask Node again. 264 divided by 60 divided 60, 24, 30, 65, 584 years. This is nanoseconds. Okay, so this is like the lower bound that we kind of support here. So this cannot go above 584 years, but we cannot check if it goes above 584 years because this will kind of overflow and it'll just drop it. So difference between max ns and we have that s to now ns is less than delta ns, then we have an issue. Now what is max nanoseconds? This is like 2 to the power of 64 minus 1, which I don't even know if can be I think the only way to like create this is like to do something like 163. So we now have a 1. We have 63 ones, and then we shift that over and then add 1. And that's one way to construct this whole thing. This is going to be uint 64 type max is equal to that, and then now ns, and then finally we just do if we can hit this value, but we can't exceed it. So max minus s now ns is less than delta. What if it's equal to? That's fine. Then we have the issue. Out of time, but this one actually does warrant a printf. So out of time, bud. But let's wrap it up. Alright, and then we just return. To avoid minus, I'm going to do this. Cool. Alright. Alright, so now we have absolute nanoseconds, and we know that it's invalid. It's in range. Oh wait. Oh right. The whole point of this was that this could fail, so we have to do this minus thing. Yeah, we have to do. So now we can do the plus. So this is going to be now nes. What do I call it that here? Just call it, yeah, now nanoseconds. If now nanoseconds plus delta nanoseconds, that's the absolute nanoseconds. Then we take the absolute seconds and then we just schedule that thing. And all we need to do is take that requested seconds, shift it over by the amount of bits we need, absolute seconds, and I think we're good. And that's it. Yeah. Okay, cool. I think that should build now. Make test. Make sure I'm on time. One sec. Yes. Okay, we're back. I knew it would not like that, but this is actually kind of crucial. Okay, printf. You want stdio, fair enough. So, cool, down to 2 errors, 2 warnings. Undeclared max, that's fine. Where is it? Max. 93. Max nanoseconds. There we go. All right. Of course. Okay, so now it's all hinging on this number. 2 to the power of 64 minus 1. You know what? I bet there's an easier way. C, in 64, max value. Unsigned. Alright, there we go. I just need 1. Not size of. Here, no. Yes. 2 to the 60. No, I need 2 to the 64. No negatives here. U. Don't tell me. Yeah? Is that it? Okay. What is this? Boost integer. Which one? Student. uint64 max. Oh, can I just do this? No, you know what? I'm pretty confident in my calculation here, so let me just go ahead and fix it. So you want uint64 type, and let me just append that. I'm just gonna keep appending that until it works. Let's see it. Okay, well, was that it? That's all I need to do? Wait, seriously? I just need the first one to work? Alright, fair enough. Can you... let me do a check. Node. Boom. -1. You've got the right idea. Unfortunately, I do need a 1L. Oh, it's not. A big int 1. Alright. Big int 1, 63. Oh, fuck you. Big int 63. Isn't there an easier way to do this? Oh, n. Right. Okay. 1n 63n minus 1n. Minus 1n, 1n plus 1n, right? It's a beautiful number, but I'm curious. 64n minus 1n. Yeah, my math is sound here. I bet if we try to do that exactly, we get an error. Let me just clarify one. We swap that stuff real quick. What happens if we do this? It overflows, right? One more. Or no, we don't need that last one. Try this. Yeah, it overflows. I knew it. Cool, fair enough. Undeclared identifier. Okay, we need test on main. Oh, actually, that means this compiled. We just compiled that. And let me... something that's been bothering me. Can I just do this? Huh? Oh, it has to come first. Maybe... that? No, that doesn't make sense. Clean, make, test. Okay, cool. So now it like refreshes it every time, which is good. Right, test main C, what do you got for me? Yes, you should do include hashtag scheduler.h. What do you got for me? Oh, no. Not quite. Still not a... No, in the other one, not this guy. This guy doesn't do anything. Sorry about that. Test scheduler. Where is it? There we go. Include scheduler. Now we're talking. Let's see it. Beautiful. No errors. Well, definitely some leaks though, because we did not set up the actually I just want to see what happens. I want to see what happens if we try to schedule anything in this. So what's the scheduler.h, what's the route? What's the meta? Schedule fast. Honestly, I want to get rid of This is still. Damn it! Who has it open? Who the fuck has it open? 47 nanoseconds. Schedule fast, schedule slow. I don't really like that. Can we just do this? Is this a problem? Like, does anyone have a problem with me doing this? Yes. Okay. Oh. Oh, we just need to forward. We just need to forward declare it. Is all. I don't want it called. I don't want it called. We just need to forward declare it. There we go. Does this work? Believe it or not, yes. Or we could just put it forward the other one, which is probably the better idea. Yeah, let me copy all this. D20D, D25D. Okay. And I think this should work just fine. Yep. Nice. All right, let's go ahead and do that. So we'll call schedule fast. Schedule slow does not need to be called. We'll just I need this many nanoseconds out. Figure it out, okay? Bring this up just a bit. Interesting that we only need a few. Huh. Yeah, I guess that's all we need, huh? Doesn't really need much at all. Okay. Schedule fast. What do we actually want to do here? What does it take? It takes a scheduler, of course. It takes a event and a delta nanoseconds. I mean, it seems a little bit wasteful to allocate a delta nanoseconds and a delta event when they're just going to be put together, but I guess it's not the role of the caller to know the implementation of those. And they kind of come from different places anyways, so they will be created differently, I think. Let me just add a note, I guess. Maybe take one UINT64T as a param. There we go. Schedule fast. What are we scheduling? Event and delta. Event can be fucking anything. Man, I'm struggling to think of a number. Events is equal to delta nanoseconds is easy. We can just do 100. This is a number. There. I don't know. Event. Does this return anything? It's a void. Do we need to return anything? A boolean? If we run out of time? Well, we run out of time. If the bucket overflows. If the bucket count ever reaches the max value, we're doomed. Yeah, whatever. So let's try this. We just return a uint64, so uint64 scheduled scheduled is equal to sh pop. Yeah. And this will get from whichever slow or fast schedule we need, and we'll just do printf scheduled. Oh, sorry. What is this? Hello, you. Let's see what happens. What? Oh, sorry. Little warning there. Seg fault. Well, that's good. Because we didn't allocate anything, did we? The basic test fails completely. Okay. What do we actually need? Let's take a look at what is in the source. So cat includes, and we'll actually modify it here. So we need now, which is oh, right. Then we need 4 things, I believe. Well, this one's easy. Now is equal to 0. Current bucket is equal to 0. Slow bucket is equal to PQ in it. And priority queue, I believe, takes a capacity, which I'm kind of iffy about. Yeah, I don't like that it has a capacity. I think it should be automatic and just double as we go. But whatever, we'll do 1024 for now. I mean, there can't be like 1,000. I mean, this. Whatever. That's a slow bucket, and then we'd need to do 4 int. Yeah, I can just do int I is equal to 0, I is less than scheduler buckets I plus plus. So for each 8 bucket, we're gonna do. Oh, right. Buckets. Oh, PQ doesn't even have capacity. Wait, how the fuck is it? Oh, right, because it's stored differently. Okay. PQ buckets. Buckets is equal to malloc buckets times bucket times size of PQ star, and then buckets I is equal to malloc size of PQ star, I believe, and then we just do returns. And then here makes it a bit more interesting. Let me just copy what we allocated just so I remember. We probably want to do something very similar, so we don't need to deallocate these. Slow bucket needs to be freed, so free slow bucket. That's an easy one. Alright, it's PQ free. PQ free. Yeah, free SH, that one's fine. This one's free the buckets itself. We should call it fast buckets, and then we need to do something like free. Oh no, these are PQ. So PQ free. Is it just this? Maybe. I think that's it. Okay. Yeah, this is a slow bucket. This is a bucket. This is this thing, and then this is the thing holding all those things. Cool. All right, let's try and make tests. Okay, cool. You did not like that. On line 12, of course. There. Okay, segmentation fault. Okay, well this is kind of interesting because I don't remember coding a segmentation fault. So let's see exactly where it happens. So we have Is it the free? Or is it the pop? Or is it the schedule even? Okay, the schedule is enough to get a segmentation fault. Alright, let's dive in. I didn't realize we were testing edge cases, but here we are. But let me just do this. Git add dot git commit finally compiles with extra bugs. 530. Shit. What do I need? Okay. Cool. Let's see if we can just solve this one bug, and then I'm probably gonna head out. So, so somewhere in scheduling fast it completely fails. So let's add some trace to see what's going on here. Make test. Segmentation fault. Out.test. Doesn't say where though. Schedule fast. If I had to guess where it's going, well, we're probably not doing schedule slow. Also, there's so many damn comments. I need to figure this out. It's probably here. Probably in this one. This is the most consequential one. Printf about to push. Pushed. Yep. Okay. So it's PQ pushing that's failing. Now, why would that be the case? Why would that be the case? Let's add some more information. PQ push should be able to handle UN64s. That's the whole point of it. Yeah, UN64. So the problem must be, I don't know. Maybe it's an invalid PQ. Push to resulting buckets. What do we got? About to push to 0. That makes sense. Did we SH buckets I is equal to malloc size of PQ? Oh, right. It's not that simple. We actually want a PQ in it. We use PQ free. We want, I don't know, fucking 1024. Okay, next thing is to rip that 1024 out from the fucking roots. And there we have it. And it seems to be stuck on something else. Okay. Pushed. This one looks fine. What's going on with the... Okay, well, clearly something in pop is not happy. What's going on with pop? Pop, what's going on? Okay, I do see a while loop here, but is if PQ is empty, buckets, current bucket, and bucket mask. Did we not set current bucket? I don't get it. Okay, let's try this. Let's see if it's empty. PQ is empty. PQ number D is empty. There's going to be current bucket and bucket mask. Let's see what happens here. Alright, well, it's not that. Checking. Well, we do get here, right? That's not the problem, right? Checking bucket number 0. Okay, that's fine. That must be another while loop. So, oh, okay, here it is. If peak. Oh, wait, no. If we only pop once, it shouldn't be a problem. Also. Yeah. Okay, so we explicitly put a funny one of these guys in, and I think we just reached this statement. Okay, peak TS. What if it's empty? If the slow scheduler is empty, could be possible. Could be possible. I don't think it will be if we start doing end of month events, but we could do if, now that we have PQ is empty, PQ slow bucket. Then we do this. Or yeah, if it's not empty, then we do this. And there's only one, we don't need to loop through anything. And we do have quite a level of indentation here that I'm not a fan of, but do this. There. We just re-peek it again, and then we can get rid of this, this, and this, and that, and then there. Let's see what happens. Nice. What the fuck is that? What is going on there? What the fuck is that? Completely mangled it. Completely mangled it to shreds. Okay, well, it is one of these guys, but let's do this. Printf now set to okay, there's that number. Okay, now set to 100. So we're 100 nanoseconds in, which makes perfect sense. But why is this getting so clobbered up? Like, this should at least be... What is... Oh, wait. Okay. Okay, I think I see. Let me try something real quick. This... sorry. Node. This minus 1,000, right? Still looks like a weird number, but if we did, check this out, divide by 2, divide by 2, divide by 2, oh, shit. No. There. Which oh, because next now has the priority in it, right? Let's break this up. Let's take a look at this thing. So this is the binary string. If we do, so first of all, there, that's a 64-bit, so we're basically looking at something like this, okay? So what we got here is there. This right here is 31 bits. There. 38. So this is priority. This right here is priority. 1, 1, 0, 0, 1, 0, 0. So that is 1, 1, 0, 0, 1, 0, 0 dot parse int 2. Throwing a B in there. Oh, that's 100. I know it's kind of weird because it's all ones and zeros anyways, but still. I'll use a better example next time. Then we have that 111. That's the type. That's the type right there. And then after that, we have the event. What is this exactly? I'm going to let you guess. But this is, in fact, 1000. And I'm actually pretty happy with this. But I got to go right now. So, cool. Ooh. Cool. Git add source, git commit. I'm curious to see what the diff was on that actually. All right, fine. Don't tell me. Bug fix, no infinite loops, please. Git push. I really should put this on GitHub, but git log p just so I can see what changed there. Okay, so we properly allocate. We added some print statements, and we stopped an infinite loop. Cool. I think I'm actually. That's pretty cool. That's pretty cool. This whole thing represents. This represents when to run it, and this represents what it is, and this represents some parameters. I think we're actually kind of ready to test this, and just hope we don't get any errors. Now, with this created, let me just make a note. Next step, rip out 1024 from priority queue and other hard-coded capacities. Yeah, like the free list.